So today we're going to be breaking down different expressions in a different way, still using basic trig functions. Now, one of the most useful tools that you can come up with is a lot of students, when they first look at sines, cosines, and tangents, they look at them as this thing. Oftentimes, when they look at the sine of x, they look at it as almost a sine times x. And one of the things that we do try and break that habit early in is getting them to recognize that sine of x is just like any other expression that we can deal with. So if I ask you to factor something, we're going to treat, in this case, like the secant squared of x, just like another variable. So without further ado, let's jump into this and see what exactly is going on with that. So when I see the secant squared of x, we said that we're going to look at this as another variable. So quite literally, one of the first things that we're going to be doing is learning to treat, let's say, the secant of x as a variable. So let's treat it as like a u. And so I'm going to substitute in this u into this expression anywhere where I see a secant squared of x. So what I see right here is I see a secant squared of x minus 1 all over the secant of x minus 1. And just like we said, I'm going to substitute this in as a u. So when I look at factoring this expression and reducing it, this is a lot more familiar and a lot more friendly than trying to maybe associate this. Now, will you always be expected to rewrite it as u squared minus 1? No, but it's going to, in essence, work the same way. So if I see something like this, the first thing I know is that's a difference of squares. So my first step is to write that as a u plus 1 and a u minus 1. On the bottom, I have u minus 1. I notice those two expressions cancel out, and I'm left with u plus 1. Now, you might be tempted to say, here's my final answer, and box it up. But remember, we did a substitution, so at the end, we need to make sure that we undo that substitution. So therefore, I get the secant of x plus 1, and that is our final answer. Awesome. So we see how these trig functions work the same as many other areas of, I'm guessing you would just call this algebra. We're going to treat this one the same way. Now, I don't see a secant, so I'm going to say, how about this time we take the sine of x and replace that with a u. So anytime I see sine of x, I pop in a u instead. So 3, sine squared of x minus 5 sine of x minus 2. And when I plug that in, boom, I have this. And I can look at that and say, this is a quadratic. Very straightforward. I'm going to come over here, and let's do this in green where I do the other work. Take first times last. That gives me a negative 6. Negative is going to be a difference. 1 and 6, 2 and 3. 1 and 6 give me a difference of 5, give me a difference of 1. I'm looking for a 1 and a 6. So therefore, 3u squared minus 6u plus 1u. That turned into a y, let's ignore that, over 2. 2 GCFs, 3u, no GCF over there. So 3u gives me a u minus 2. u minus 2. So I have u minus 2 and 3u plus 1. So again, we factor that the same way we'd factor a quadratic. But because we've previously inserted a substitution, we have to undo it as well at the very end. So anytime we see this, we're going to say, okay, minus 2 plus 1. Sine of x, sine of x. And that is our final expression. There we go. So having seen two examples where we can treat trig functions just like any other function, why don't you go ahead and pause the video on number 5, unpause it when you're done, and see how well you did. Awesome. Okay, so now that you've had a chance to try it out, you notice that in this case we have the cotangent. So I'm going to go ahead and I'm going to rewrite the cotangent of x as a u again, which means I need to plug it in, not 1, not 2, but all 3 of those spots. So I have the cotangent cubed plus the cotangent squared plus the cotangent plus 1. So I need to substitute once, twice, thrice. In this case, I'm just going to do the same thing, factoring by grouping. u squared, no GCFs. So u squared leaves me a u plus 1, which leaves me with a u plus 1, and then a u squared plus 1. So I factored those out. Now again, I'm going to take this and I am going to undo the substitution that we previously did and say, okay, so this is the cotangent of x plus 1, and this is the cotangent of x squared plus 1 as my final answer. Awesome. So that brings us to my next set of problems. And so with these problems, what we're looking at is we're looking at trigonometric substitution in a different way in order to solve the equation. So I know that I have some unknown angle measure of theta, and I'm going to insert my value for x into the equation to solve for the sine of theta and the cosine of theta. Now let's take a look at what exactly is going to be going on in this style question. So let's do this one in red. So I'm going to take that and I'm going to plug it straight into my expression. So if I have something like 9 minus this, okay, I'm going to take the 3 cosine of theta and plug it straight in. Now at this point, this is going to be just like solving any other equation. I'm going to go through the same process, get rid of powers. So I'm going to square both sides, which is going to leave me with this squared is going to be 3 times 3, root 3 times root 3, and 2 times 2. It's going to get rid of the root above here, so I'm going to be left with 3 cosine of theta squared, which I'm going to go ahead and then square itself. And then at this point, I'm going to go ahead and I'm going to start simplifying some things. Now, the first thing I notice is all 3 of these have a 9. I can just get rid of the 9 by dividing both sides by 9. So I divided. Now, this is a little easier to work with. So cosine squared of theta. If I subtract a 1, that gives me a negative 1/4. So cosine squared of theta is equal to 1/4. And if I square root it, the cosine of theta, I've artificially introduced a square root, so I get 1/2, positive or negative. Now, this piece right here is going to help me solve for the sine and the cosine of theta. Now, I know that because the cosine can be either positive or negative, technically speaking, I could fall into any of the 4 quadrants, because I know cosine is positive in these 2 and negative in these 2. So if I'm dealing with positive or negative, I'm pretty much just out of luck. But luckily speaking, we have this restriction where theta is somewhere between 0 and pi/2, which means theta is somewhere in the first quadrant. So if I go ahead and I draw it, let's not do that in, let's do that in red. So cosine, we know, is going to be x over r. So if my x is 1 and my r is 2, well, that's going to be a, let's see, opposite one is 30, 60, 90. That's a 30, 60, 90 triangle, which is going to help us solve for the sine of theta and the cosine of theta. Sine of theta is going to be opposite of our hypotenuse, which is root 3/2, and the cosine of theta is going to be 1/2. Boom. There we go. So let's slide off to the next question. Now with number 9, we're going to do the exact same process. We're going to take our value, 2 secant of x. I'm going to plug it directly in to where I see the variable. So I get the root minus 4 equals 2 root 3. And what I've plugged in is 2 times the secant of theta. Oop, that's all squared. I'm going to solve this like I would solve an equation to go ahead and try and isolate this secant of theta, which is going to be my clue to solving for sine and cosine. First thing, I'm going to square both sides, which is going to leave me with a 2 times 2 is 4, root 3 times root 3 is 3. If I go ahead and square this, that will give me a 4 secant squared of theta minus 4. There's no root anymore because I squared both sides. Again, I see that all of them share 4, so my secant squared of theta minus 1 is equal to 3. I'm going to add my 1. Secant squared of theta is equal to 4, and then root it. So secant of theta is equal to either positive, negative 2. Awesome. So that secant of theta, we know, has to deal with the cosine of theta. And if cosine tells me x over r, this is telling me r over x. So if I'm dealing with my limited quadrants right here, I know my x value is an understood 1. My radius is a 2. Hey, and this is the exact same as what we saw right here. It's going to give me a root 3 because this is a 30, 60, 90 triangle, which tells me that my sine and my cosine are also going to be exactly the same. Sine is root 3 over 2, cosine is 1/2. Awesome. So now that you've seen 2 examples of that, why don't you go ahead and try out number 11, pause the video, unpause it when you're done, and see how you did. Okay, so let's see how we did with that. Now, I'm going to go ahead and I'm going to plug in the 2 sine of theta straight into there, which gives me root 2 equals root 4 minus this thing squared. So 2 times the sine of theta. And I'm going to go ahead and I'm going to start trying to isolate this, which means I'm going to square both sides. And I'm going to square this on the inside. So 4 sine squared of theta. No root because I did square both sides. Next thing is I'm going to subtract 4. Divide by negative 4. And then root it. Now when I take the root, I have positive or negative. Square root of 1 is 1. Square root of 2 is root 2. Now, normally what I would do is I would go ahead and I would try and rationalize this. But again, we're not too worried about rationalizing this because it's going to tell us the relationship of 2 sides of a triangle. Okay, so sine we know is y over r, so my y is going to be 1, and my radius is going to be root 2. This is a 1. Well, guess what? This is a 45, 45, 90 triangle, which means that's also going to be a 1. So my sine of theta and my cosine of theta are going to be the exact same thing. 1 over root 2 or root 2 over 2. Cosine is going to be 1 over root 2 or just a root 2 over 2. And there we go.